In this video, we are going to start delving into the details of the Higgs mechanism. In particular, let's consider an SU2 sub L. In particular, we are going to consider an SU2L doublet of complex scalar fields, which is the Higgs scalar field. In particular, we define phi of x to be phi plus of x and phi 0 of x. So this is a scalar, and it is a complex scalar field, as well as this one. Okay, so they are complex scalar fields, whereas phi of x here is a doublet of scalar fields, complex scalar fields. Consider the Lagrangian related to this Higgs field. In particular, let's write down a Lagrangian of the following form: d mu phi dagger d mu phi minus v of phi, where v of phi is a potential, which we write like this: v of phi is mu squared. I will tell you about this constant mu. Phi dagger phi. So this is a constant, to not be confused with this index mu here. And phi dagger phi is the mode of phi squared. And then we also have plus h, which is another constant, phi dagger phi squared. So in particular, this one will be phi to the fourth, mod phi to the fourth. Mu squared is less than 0, and therefore it means that mu is, it is an imaginary number. If mu squared is less than 0, it means that basically mu is equal to a constant, a real constant, c times the imaginary unit I, in order for it to give a negative result when we square it, right? But we take this into account, and we also set h greater than 0, right? Now, if we consider the derivative of the potential with respect to the mode of phi, well, what we get is 2 mu squared mod phi plus 4h mod of phi cubed. Now, since mu squared is negative, it means that this expression here has a minimum value. So if we set it equal to 0, we find that the minimum value for phi, so we call it mod phi 0, is equal to the square root of minus mu squared divided by 2h. Simple as that. And we define this to be v, another constant, which is greater than 0, divided by the square root of 2. So this value here is the value at which the potential is minimum. And it is greater than 0, as you can see. So the minimum value of the potential, V min, is equal to V evaluated at the mode of phi 0. Right? So it is equal to, if we check, it is just mu squared times this one squared, so v squared over 2, plus h, v to the fourth divided by 4, and this is equal to, since from here you can see that minus mu squared is equal to v squared h. So if we use this equality in here, we can see that this is equal to minus v to the fourth h over 2 plus h v to the fourth over 4. So this is equal to minus h v to the fourth over 4. If we consider interactions, so in particular, if we consider the fact that this Higgs field can interact with W tilde mu, so the W boson and also B mu, and if you recall, of course, B mu and this W tilde mu, they are related after we rotate, after we use that rotation by the angle theta w, which is the Weinberg angle, remember that these are related to the photon field, the W boson, and the Z boson. But we started from this, if you recall. Now, when we consider these possible interactions, the Lagrangian, of course, will be written with the covariant derivative. So d mu phi dagger d mu phi minus v of phi, like this. And the covariant derivative, so if you apply d mu to phi, so that you can also put the upper index there, this is d mu plus ig w tilde mu plus ig prime y phi b mu applied to phi. So this transformation is due to the fact that phi is an SU2L doublet, right? So it can interact with the W boson and also B mu with the with this B mu here. Just like in the previous videos where we had doublets and we had this type of interaction. So we had this type of let's say fields entering into the expression for the covariant derivative. Now LH, if we use this definition for the covariant derivative, will be LH will be invariant under local transformations, and these local transformations are related to the group SU2L tensor product with U1 of Y. Now we know that this subscript Y is related to the hypercharge, which is this Y phi here. Also, there is an infinite set of degenerate states with minimum energy, because the equation that we derived in here, so phi mod phi 0 equal to v over square root of 2, this equation can be satisfied in many ways by the components of phi. Remember that the components of phi are phi plus of x and phi 0 of x, and remember that these are complex scalar fields. So if we want to write this in terms of real scalar fields, we can write it in the following way. So we can put a constant here for the sake of convenience. This constant is 1 over square root of 2. Then here we have phi 1 plus I phi 2, and in this case this phi 1 and phi 2, they still depend on x, but they are real scalar fields in this case. And then we have phi 3 plus I phi 4, like this. So this equation, mod of phi 0 equal to v over square root of 2, if we use this definition for phi, can be written in the following form. So mod, we can write it in the following way in particular. Mod of phi 0 squared is equal to v squared over 2. The mod squared can be calculated from here. So in particular, we take phi 1 squared plus phi 2 squared plus phi 3 squared plus phi 4 squared. So this is how you calculate the mode of a doublet of complex scalar fields. So we take the mode of the first one squared, which is phi 1 squared plus phi 2 squared, and then we add the mode of the second complex scalar field. Of course, this is divided by 2, so we have 1 over 2, because we have to square this 1 over 2, and this is equal to v squared over 2. So we can get rid of this factor of 1/2 from both sides, like this. So this is the equation that should be satisfied, let's say, in the degenerate states. So the degenerate states should satisfy this relation. And V is a constant in our case, right? So we have to think that V is a constant and it is related to the constants mu and h, which are fixed in the theory. So this is equal to a constant. And you can think that if you sum these squares, there are definitely many ways such that their summation is equal to a constant, right? Now we can break the symmetry of the minimum energy state, or simply ground state, and we can set phi 3 0 equal to V. So if we do this, phi, in particular, we said that, I mean, the other components, phi 2 0 is equal to phi 1 0, which is equal to phi 4 0. They are all equal to 0. So phi can be written in this form, 1 over square root of 2, 0 V, like this, and this is phi written in the degenerate state, in one of these particular degenerate states, and it has this form. It can be written in this form. So we have chosen one particular state by breaking the symmetry. Now, a generic state phi can be obtained by introducing four parameters, right? Because phi is described, after all, if you think about it, by four parameters. In this case, phi 1, phi 2, phi 3, and phi 4. It was written in this form, but we need four parameters to be able to span all the different possibilities. Now, we can also write a generic phi in this following form: e to the I sigma I over 2 theta I x, and do not get confused between this I and this I here. So we are summing over I for these two variables. In particular, sigma I are the Pauli matrices, and this theta I of x are three parameters: theta 1, theta 2, and theta 3. Then we have 1 over square root of 2, then we have 0, and then here we have v plus h of x. So v is a constant with respect to x, but here we add another parameter. So we have three parameters here and another parameter here. So we still have four parameters, and this is a generic state because we have four parameters which are capable of describing an SU2L doublet. Now, the local SU2L invariance, the local invariance allows us to rotate the system such that the dependence upon these three parameters here is eliminated. So what I'm saying is that we can rotate the system in such a way that we can eliminate these parameters. They will not appear. This means that our state phi can also be written in this form: 1 over square root of 2, 0 v plus h of x. And this is permissible thanks to the local SU2L invariance. Now, let me go back to the expression for the covariant derivative that we defined. In here, if you recall, we had these parameters g prime, which are the usual parameters, the couplings. Then we also have the hypercharge y-phi. We called it y-phi, which is related to phi. And remember, we used local gauge invariance in such a way that we could write phi in this form by removing these three parameters. Thanks to the SU2L invariance, we can remove those three parameters, and therefore we can write phi in this form. Now, remember that for the hypercharge y-phi, we have the following equation. We have Q. In general, we have minus sigma 3 over 2, right? If you remember from the previous lectures, and in particular, instead of sigma 3 over 2, we write t. We have the operator that we called t. Now, in this case, since this first entry in phi is equal to 0, we are only focused on this second entry. So what I'm saying is that instead of considering the matrix here, we should actually consider one of the eigenvalues, and in particular it is the eigenvalue associated to the second entry of the doublet. And in particular, the second eigenvalue for sigma 3, if you recall, is -1. So the second eigenvalue for sigma 3 over 2 is -1/2. So we can write this as q plus 1/2 basically. And as I said, this is due to the fact that we have an SU2L doublet and we are considering only the second component of phi. Now, since we want to impose that, so what we require is that the Higgs boson has zero charge. So we want Q equal to 0 for the Higgs boson. And we obtain, therefore, Wi-Fi equal to 1/2. So we can use Wi-Fi equal to 1/2. We are going to use one more time the expression for the covariant derivative, because now we want to rewrite the Lagrangian. Remember that in the Lagrangian we have the covariant derivative which appears like this: d mu phi dagger d mu phi. And d mu phi dagger d mu phi is the mode of d mu phi squared. So we can also think of it in this way. So now what I want to do basically is exactly this. I want to write, let me zoom in, I want to write d mu phi mode squared. So if we use the definition for phi, in this case we are going to use 1 over square root of 2, and then the first entry is 0 and the second entry is v plus h of x for phi of x. And of course, for the covariant derivative, we are going to use the same definition that we used last time. Here, in this kind of notation, I can put this mu either in the upper position or in the lower position. Doesn't change. The mode squared will still be the same. Just to let you know that. So here, if we calculate this, we have 1/2, then we have mode, we have d mu plus ig w tilde mu plus ig prime times 1/2, and this 1/2 comes from Wi-Fi d mu, and then here we have 0 v plus h mode squared. Now we can replace, so we can substitute, instead of w tilde mu, remember that we already calculated this a couple of lectures ago. I don't remember exactly when, but we did it. It's a very straightforward calculation. This is w mu 3 in the first entry. Then here we have square root of 2 w dagger mu. And here we have the square root of 2 w mu. And then here we have minus w mu 3, like this. So we can substitute it, we can replace it in here. And you have to think that this d mu here should be d mu times the identity matrix in 2 dimensions, because now if we replace w mu tilde with this matrix, 2 by 2 matrix, you have to think that these are actually multiplied by the identity matrix in 2 dimensions. So we can write this as 1/2 mode. We have mode of d mu plus ig prime over 2 b mu. So it comes from here. And then we have plus ig w mu 3 over 2, right? And then we have ig square root of 2 over 2 w mu dagger. So in this case, we don't have anything else for these entries here, because we have this from this matrix. But since these are multiplied by the identity matrices in 2 dimensions, we only have this contribution multiplied by 1/2, and of course ig in this second column. Down here we have Ig square root of 2 over 2 W mu, like this. And down here we have d mu plus Ig prime over 2 B mu minus W mu 3. Sorry about this, let me write it properly. W mu 3 over 2 times Ig. Like this, and of course, here we have the vector 0, v plus h, and then we have to take the mod squared, like this. So now we can multiply this matrix with this vector. We have 1/2 mod of, here we have a vector whose first component is Ig 1 over square root of 2 W mu dagger v plus h. Then the second entry is d mu. So the derivative is only going to act on h because v is a constant. So we have d mu h plus I g prime over 2 b mu minus g w mu 3 over 2 v plus h, and this is the vector. So the first entry is this one, whereas the second entry is of course this one here. So I have just multiplied, for the second entry I have multiplied this by 0, which is of course 0, and then we have this by this, which is exactly this, if you check. So I have factored out, I have factored out I, and I could have factored out also this factor of 2 here, and I could have put it here, but never mind. And then I have to take the mod squared, right? And now we are ready to take the mod squared. It's quite simple. We have 1/2. Then we have g squared over 2 W mu dagger W mu from the square of this. And I also have v plus h squared plus d mu h d mu h. So this is the square of this first term. So when you square it, when you take the mod squared, this is what you're going to get. Remember that h is a real scalar, so h is real. Therefore, when I take, in general, I should have considered d mu h times d mu h dagger, like this. And of course, this is equal to d mu h dagger, like this. But now, if h is real, we have d mu h, like this. So the important thing to stress is that h is real, so we can write it like this. Then we also have plus 1 over 4 g prime b mu minus g w 3 mu. And we also have g prime b mu minus, let me zoom out, minus g w3 mu. So for example, this w mu 3 with the upper mu and the lower 3 is defined to be simply w3 nu era nu mu, like this. And then this is multiplied by v plus h squared. And that's it. So this is the mod squared of this expression here. Now we can also rewrite this term, in particular g prime b mu minus g w3 mu is equal to, now you can you have to remember the fact that g prime is equal to g times the tangent of this angle theta w, which is the Weinberg angle. Theta w is the angle by which a spontaneous symmetry breaking rotates the WB boson plane to produce the Z boson plus the photon. So basically you have to remember that W is a vector, so we have three components for W mu, and we have one component for B mu. So of course B mu can take different values, B0, B1, B2, B3, because this is the Lorentz index. But you have to think that there is one particle associated to this B mu boson, B mu field, which produces bosons. Its excitations are bosons. And from B mu, and one of the components of W mu in particular, I'm talking about W3. So the component is exactly W3, if you recall. If we use this relation, we can write this as G times sine of theta W B mu minus cosine of theta W times W mu 3, like this, and then we divide, of course, by the cosine of theta W here. Now we have to remember that W mu 3 and B mu can be obtained by a rotation of this kind, cosine of theta W sine of theta W minus sine of theta W cosine of theta W, and here we have the vector Z mu A mu. Or if you want, if you invert this matrix, you can write Z mu A mu as another matrix cosine of theta W minus the sine of theta W sine of theta W cosine of theta W. So this matrix here is equal to the inverse of this, which is also equal to the transpose of this matrix. So this is a unitary matrix, and in particular it is an orthogonal matrix in this case. And here we have W mu 3 B mu like this, and if we calculate Z mu, you can see that it is equal to the cosine of theta W W mu 3 minus the sine of theta W B mu, like this. And now if you check, what do we have there? We have minus G over the cosine of theta W times Z mu. You can see it from here. Simple as that. And therefore, when you consider the product of this times this product is going to give you G squared divided by the cosine squared of theta W Z mu, like this, right? Therefore, we have shown that d mu phi dagger d mu phi, which is part of the Lagrangian, this is equal to 1/2 d mu h d mu h. So remember from here we have 1/2, and then we have this, and then we have plus v plus h squared, then we have g squared over 4 w mu dagger w mu, and then we also have plus g squared over 8 cosine squared theta w z mu. This is the expression that we find. You can see, I mean, that the algebra leads you to exactly this expression here. It's very simple, and this is a very important expression that will allow us to generate the masses for the W and the Z boson. So now I have written down the mathematics, so this is the formula, and next time, in the next video, we will finally do some considerations starting from this formula, and we'll see how the masses of the W boson and the Z boson appear. In particular, you have to check this part. This is the important part that gives masses to the W and the Z boson. This part is related to the mass of the W and the Z bosons. So let's consider the Z boson. In particular, you can see that Z mu appears here. So this is where the Z boson appears, and this quantity is multiplied by this constant here, g squared divided by 8 cosine squared theta W, and it is also multiplied by this. If we set 1/2 mz squared, so this is the mass of the Z boson, and we set it equal to v plus h squared g squared divided by 8 cosine squared theta W, and we let h go to 0. So basically we are going to cancel this contribution here. From here we get mz equal to g times v divided by 2 cosine theta W. This is exactly the mass of the Z boson, and I want to tell you something more about this. Now, the mass appears like this in a theory, in a scalar field Lagrangian in particular. Remember, for example, the Lagrangian for a scalar field. So for a scalar field, we have Ls, where S stands for scalar. This is 1/2 d mu phi minus 1/2 m squared phi squared. So here you can see that we have phi squared, which is a term of the second order, just like this one. And here we have 1/2 the mass squared, right? So this is how the mass appears. In this case, we have terms of the following kind. So we have, if we take this part multiplied by v plus h squared, so we have v plus h squared g squared divided by 8 cosine squared theta W, and then z mu can be written as z0 squared minus z1 squared minus z2 squared minus z3 squared, like this. So you can see that if we consider the Lagrangian in particular, we can call it L. So it is a Lagrangian which can contain also other interactions. So not only the field phi, but also other fields. If we take the derivative of that Lagrangian with respect to Zj, and we take the derivative twice, so we have dzj squared here, we have d squared here, and we put a minus. So j, in this case, should be interpreted as an index which can be either 1, 2, and 3. So you can see here that we have these minus signs. So when you take this derivative, the second derivative, what you get is, you can see it here, you get v plus h squared g squared divided by 4 cosine squared theta W. In this case, this is the mass of the Z boson squared. So in general, if you are considering a specific field, here you have the mass squared. So you can define the mass like this, and you have to turn all the fields off. So it means that the fields should be set equal to 0 if you're going to consider this formula here. So let me give you some more examples. This is how we can calculate the mass in general. Now for the W boson, which is a complex scalar field, the 1/2 factor does not appear. I mean, you can see that we also have the factor of 1/2 in the real scalar field, but if we have a complex scalar field, the Lagrangian for a complex scalar field can be written in this form: d mu phi star d mu phi minus m squared phi star phi. So in this case, the mass, you can see, I mean, you don't have the factor of 1/2, so you can define the mass squared, as the derivative, the second derivative of the Lagrangian, and then you have to take the derivative with respect to phi and phi star. You put a minus, and you turn all the fields to 0. And this is how you get m squared. And what about the mass of the W boson? We can do the same here. So basically we have to take a second derivative, and the first derivative is taken with respect to W mu, and the other derivative is taken with respect to W dagger mu, right? And what you're going to get basically is this factor in front without the 1/2 that you got from here. So mw squared is equal to v plus h squared, but remember that you're going to set the fields to 0, so h is going to get, is going to be equal to 0, so you get v squared. So by setting h to 0, you get v squared g squared divided by 4, and therefore mw is equal to vg divided by 2. And this is the mass of the W boson. You can see from this formula and this formula here that mz is equal to the mass of the W boson divided by the cosine of theta W. So the mass of the Z boson and the W boson, they are related, as you can see, thanks to this formula here that we just wrote down. Also, we can write down the mass for the Higgs boson. In particular, remember the Lagrangian for the Higgs field. Lagrangian for the Higgs field is this one. Let me do some manipulations. LH is equal to d mu phi dagger d mu phi minus v of phi, which is this expression here, so it is minus mu squared. Then we have phi dagger phi minus h. Then we have phi dagger phi all squared. This is equal to, now remember that in the vicinity, in the neighborhood of the minimum energy that we have chosen, the minimum energy state, phi is equal to 1 over square root of 2, 0, v plus h, like this. So we have broken the symmetry, and we have chosen this minimum state, where in the minimum state you have h equal to 0, so you only have 1 over square root of 2, and then this vector becomes 0, and the second entry is just v. Now if you put it there, you have 1/2 d mu h minus mu squared over 2 v plus h squared, and then we also have minus h over 4, because this expression here is equal to the mod of phi to the 4th, so you get a factor of 4 here, which is the square root of 2 raised to the 4th power. Then you get v plus h to the 4th, right? Now we can define, as usual, the mass squared of the Higgs boson as minus the second derivative of the Lagrangian with respect to h twice. So it's with respect to h, and this is the second derivative. And remember that we have to set all the fields equal to 0. So in this case, if we take the derivative of the Lagrangian of the Higgs field, we only have to turn off the field h. So we have to set it equal to 0. We have to set this field equal to 0. If you consider only the Higgs Lagrangian, so the Lagrangian for the Higgs field, the only field that you have to set equal to 0 is the Higgs field here, because there are no other fields that appear in the expression for this Lagrangian. So if you do the computation here, you're going to get the following. So you get plus mu squared plus 3hv squared. And remember that minus mu squared is equal to hv squared. So this is equal to 2hv squared. And therefore, mh, the mass of the Higgs boson, is equal to the square root of 2hv, like this. Therefore, we have found a clever way of giving masses to the carriers of the weak force, the W and the Z bosons. You must notice that the photon remains massless, even after this symmetry break. So also after the introduction of the Higgs field.